To me, what's been happening in research on vibrotactile rendering in the last years is really, really exciting. So using vibration, we're able to render realistic surface textures where there are none. We're able to provide a button with arbitrary affordances by creating virtual force pressure curves. We can even render textures in real air or create hyperobjects which have virtual tactile gestural affordances. We can make rigid displays appear compliant, including the compliance of the ground we walk on to create virtual grounds in virtual and augmented realities. We can make hard objects appear soft. We can create virtual experience of bending and torsion, and generally design the material properties of the objects and devices we interact with.
Like, it's just so exciting. It's really, really, really exciting.
How is this possible? Well, material experiences are created through interaction. For example, when I lift a cup, I apply pressure to the cup. Based on the tactile feedback I receive, I'll modify my grip, again leading to new tactile experiences. This closed-loop behavior enables material experiences to emerge. So let's turn on the audio for some of these videos I just showed. In these videos, the vibration is presented as audio. You'll notice that there is similarity between how these systems sound, even though they're created by different research groups at different times. The reason for this is that all these systems provide vibration with a common structure. Vibrotactile impulses are synchronized with user actions. Specifically, when the user acts, this action is sampled. Signals are generated accordingly. Based on this tactile feedback we receive, we will modify our actions, which again is sampled and leads to new vibrotactile feedback. This augmented closed loop enables virtual material experiences to emerge. Let me explain this with a concrete example. Let's say we wish to add friction to a slider. We would first decide upon fixed points at which to trigger pulses. Then we sample the movement of the slider in real time with an analog sensor. Whenever one of these trigger points is crossed, we play back a vibrotactile pulse. This way, the motion of the slider is transformed in real time into a vibrotactile signal which is experienced as friction. These systems are non-trivial to implement, as they require both high analog resolution on the output signal, as well as high temporal resolution with regards to sampling human action and generating corresponding vibrotactile feedback. To make such a system more accessible to the general public, and because we need this type of device for our own research, we created what we call haptic servos. Haptic servos are self-contained embedded platforms that create vibrotactile signals based on human actions. So using one of our haptic servos, any of the systems I showed at the beginning, any of those videos, they can be implemented in a matter of minutes. The haptic servo samples human actions using an analog sensor. This can be considered the servo's control signal. A microcontroller generates corresponding output signals, which are amplified to drive a haptic actuator. The human then closes the loop. We minimize system latency by removing all non-timing critical elements. For example, changing the parameters of the haptic signal is done asynchronously. A fun feature we implemented is that haptic servos respond to pulse control, like a regular servo. You can find more information on that in our paper. Haptic servos are open source. You will find the link to the GitHub repo at the end of my presentation. They are prototype devices, but we have successfully used them in a bunch of projects. One of them will be presented by Nihar Sabnis here at CHI, and the other was presented at Augmented Humans, and all the others are still kind of ongoing. However, as I'm saying, they're prototype devices, so they come with a bunch of limitations and they're not perfect in any way. And we hope to address many of these in the future. And they're open source, so we invite anyone interested to collaborate with us in making them better. Or if you want your own version, they are open source. You can fork our repo and replicate it, modify it, and create your own devices based on our work. So in addition to this hands-on open source contribution, this project also points towards other interesting facts about perception. One of them is it appears that a broad range of vibrotactile effects actually rely on the same underlying perceptual mechanism. Vibration, proportional to changes in human action, seems to be the way we expect tactile information to be organized so that we can make sense of them as a material property. It is also interesting to note that the final experience is driven by the human action which is augmented. For example, changing input from isometric to isotonic has a much larger effect on the resulting experience than manipulating any parameter of the vibrotactile feedback. We discuss this in much more detail in our paper. To us, haptic servos are the beginning of creating an infrastructure which allows us to experiment and design with material experiences. We're super happy that we're not only presenting the output of our research, but also the tools which we created for ourselves to conduct research. And it's our sincere intention and hope that others will benefit from this. So I'm looking forward to chatting with many of you in person at CHI. This is work by the Sensory Motor Interaction Group at the Max Planck Institute for Informatics. My name is Paul Strohmeier. My fellow research group members Nihar Sabnis, Dennis Wittchen and Courtney worked on this with me. We also had support with our neighbors of the HCI lab of Saarland University, in particular from Jürgen Steimle and Narjes Pourjafarian. Thank you for your attention. See you at CHI.